Assalamualaikum and hi guys. Topic for today is photomorphogenesis, which is this process is for the plant development when they are respond to the light. First, let we look to their learning objective. So at the end of this topic, you need to know how actually the light able to regulate the plant growth and development. And you need to know also, okay, what is the role of the photoreceptor in order for the perception of the light. Means what the role of the photoreceptor when they are um, receiving the signaling of light. And you also need to know how the phytochrome respond to the red and far red light, how the cryptochrome respond to the blue and UVA light. Okay, for your information, cryptochromes and phytochrome is actually two types or two classes of the photoreceptor. The next learning objective is you need to understand the developmental processes that mediated by the phytochrome and cryptochrome. And the last one, you need to understand the signaling pathway by which phytochromes and cryptochromes they able to initiate the signaling cascade. Cascade means the event, the processes occur when they have the signaling of the light and absorbed by the phytochromes and cryptochromes. Okay, for the first part in this topic, okay, you need to know that, of course, the environmental factors such as light really important and they able to regulate the growth and development of the plant. So because of that, the quality and the quantity of light is really important in order to give the response to this development where the regulation of the plant development by the light we call as photomorphogenesis. So photo means light, morphogenesis means the development. Okay, as I told you just now regarding to the third and fourth LO regarding to phytochrome and cryptochrome is two types of photoreceptor, which is this photoreceptor they are used by plant to acquire and interpret the light signal. Okay, so if you can't imagine simply, can you just imagine that for the photosynthesis, okay, they require the pigment okay, to absorb the light. For the photomorphogenesis, okay, they require the photoreceptor. So when this photoreceptor absorb light, it will be change their conformational means it will be change their shape if when they receive the light and it will be initiate a signal transduction pathway. Signal transduction pathway means it will initiate the next process in order the plant able to their development. Okay, so this signal transduction pathway ultimately will be trigger a developmental response. For example, a developmental response is the seed development or seed germination. Okay, as I told you just now, okay, you know about the phytochromes and cryptochromes. Okay, for your information, photoreceptor not only have two class. Okay, in the photoreceptor, actually they have four classes. First phytochromes, okay, second cryptochromes, phytochromes, and third we call as phototropins, and the fourth one we call as only a newly identified class of photoreceptor. So if you look on your slide, every photoreceptor they absorb different wavelength. So for the phytochromes, okay, they absorb red, okay, at 660 nanometer, and far red light at 730 nanometer. It's different to the cryptochrome, which is cryptochrome detect the blue light or absorb the blue light at wavelength 400 to 540 nanometer, and also they absorb UVA light at 320 to 400 nanometer. So for the third classes of the photoreceptor is the phototropin. So if you look on the phototropin, they actually absorb a similar light, which is they absorb the blue and also the UVA light. But different to a newly identified class, which is they only respond to a very low of UVB light at 280 to 320 nanometer. Right, so if you look on the figure, okay, you may look on the two different classes of the photoreceptor. They absorb different light at different wavelength, and it will be produce this signaling intermediate, which is the process, okay, when the cryptochrome and phytochrome absorb the light. And this signaling pathway will be induced the transduction and will be makes some photomorphogenesis process occur in plant, okay, for the plant growth and plant development. Alright, for your information, that first three photoreceptor, which is phytochrome, cryptochrome, and phototropin, we call these three photoreceptor as chromoprotein. So this chromoprotein, they contain a light absorbing group we call as chromophore, okay, that attach to the protein. Catalytic proteins means chromoprotein. Okay, so apoprotein. What is the apoprotein? Apoprotein means combination of protein. Okay, they have more than one protein. And when chromophore bind to the apoprotein, so it refers as the holoprotein. So this idea actually is look like enzyme, because enzyme also is one of the protein. So when two substances of the protein combine, we call as apoprotein. When they have non-protein substance bind to that apoprotein, so we refer as the holoprotein. Okay, now we go to the first photoreceptor, which is phytochrome. So this phytochrome actually they found in all types of plant species, and they have three different versions. They have phytochrome A, B, and C. Actually, for these three A until C, they have a similar chromophore, which is they have a similar non-protein substance, but they only different at the apoprotein. Mean the protein substance may different, okay, between A, B, and also C. However, for A until C, this version of the phytochrome, they has two chemical states, which is first, they respond to the red light at 665 nanometer, and then second response to the far red light at 730 nanometer. Okay, for this slide, the most important part that you need to really understand is about the phytochromes regarding to their response to red light and far red light. Now we look on how a light signal able to reach nucleus of the plant cell. Okay, so from this process, okay, you can see that they give you one illustration and they are stated a number 1 until 6. So this is actually the processes, the steps, okay, how actually the light able to reach the nucleus of the plant. Okay, so the process is initiated by the two protein we call as FHY3 and FAR1. So these two proteins they bind at the DNA of the plant because this is in the nucleus. So in the nucleus they have DNA of plant. And when the binding occur between two proteins and DNA of plant, it causes a two production of another proteins we call as PHY1 and FHL. Okay, then what happened after that? They have the light signal from the sun, for example. So when this process occurs, the far red light will be absorbed by the phytochrome A. So when phytochrome A absorb the far red light, it will be change their conformation. So they change their shape. So when these changes occur to the phytochrome, it's allow phytochrome A bind with FHY1 and also FHL. So when this new conformation occurs, it makes this conformation able to enter the cell nucleus. So because of this process, so phytochrome A they able to initiate the plant developmental responses. Okay, such as for the growth of the plant or give the flowering response because of the light and also straining towards the light. However, if they have a lot of phytochrome A in the nucleus, it also able to inhibit the FHY3 and also FAR1. Alright, one more thing that really important in the phytochrome is about their capability as photoreversibility. Okay, so this is the uniqueness of the phytochromes. So every final exam or maybe quiz or maybe in the test, they always asking you about this statement, which is regarding to the photoreversibility. So means using a light, they able to give a reversible reaction. Okay, for example, when the plant absorb the red light, because right now we talk about the phytochrome. So phytochrome absorb only red light and far red light. So when the plant respond to the red light, it can be nullified with an immediate treatment with far red light. Okay, if you can't imagine this nullified process, okay, when the plant responds to the red light and far red light, okay, example of the simple photoreversibility is for the development seed germination. So when the plant responds the red light, it will be stimulate the germination, because right now is for the seed germination. However, they have another stage. Okay, first stage is absorb light, red light. Okay, second stage is they absorb the far red light. So when they absorb the far red light, it will be switch off the seed germination. So do you can understand? First they germinate, stimulate germination, and after that they switch off the germination because they absorb the far red light. Okay, now is more explanation about the photoreversibility. So this photoreversibility occurs because phytochrome, as I told you just now, they have two forms, which is one form absorb the red light. Another second form is absorb the far red light. First red light, second far red light. So these two forms of the phytochrome, they reach their photo equilibrium. So they achieve their equilibrium. So what happened? Okay, you need to remember the wavelength of this phytochrome. The process of photoreversibility is occur between 600 to 800 nanometer. Okay, because red light is 600 nanometer and for far red light is 730, so is equivalent to what we call as 800 nanometer. So when this equivalent occur, the plant that respond to the red light we call as, okay, or a form of phytochrome that exposed to the red light we call as red light absorbing form. So this red light absorbing form we call as PR is converted the biological active far red light absorbing form we call as PFR because far red light. Okay, now exposure to the far red light cause the far red absorbing form PFR convert back to the red light absorbing form. Okay, means this process is always like a cycle, which is always absorb light and then convert to the far red light. If they are exposed to the far red light, it will be converted to the red light. So if you look on the reaction also, okay, you can see they have PR and PFR and they have the arrow. That arrow is reversible, which is PR to PFR and then PFR also convert to the PR. So this process we call as photoreversibility, okay, of the phytochromes, and this process will respond for the seed development or seed germination, or in the bigger scope is in the plant development. This slide shows you the graph of dynamic relationship between PR and PFR form. And this graph is actually for the etiolated plant. Etiolated plant is plant that grow in the dark condition. So if you can see in the graph, you have three lines, which is two red line and one black line, which is for PR, PFR, and P total. So what you can see in the dark, PR level will be increased, okay, which is if you increase the time in the darkness, it will be increase the concentration of synthesis, which is concentration of synthesis is regarding to the rate of synthesis and also the degradation. They are equal, so it will be increased as time increase. And then if you can see they have the point where the PR can be converted to PFR, where in this part etiolated plant, it will be convert PR to PFR. So after the plant are returned to the darkness, so PFR concentration will be decrease. So if you can see, it decreased rapidly, okay, as does the total phytochrome concentration. And you can see both graph for the PR and PFR form um, actually is a irreversible chemical degradation. So this actually is only to show you that for the PR and PFR, which is PR convert to PFR or PFR convert to PR, they have their own graph, okay, to explain, okay, the theoretical of these two relationships. For this slide, we will go for the phytochrome responses, which is we can have three different responses based on the fluence requirement. So what we can see for the first one is we call low fluence responses, LFR, which is are mediated by phytochrome A and stimulated by light, okay, in the dose 1 to 100 micromole light per meter, and it's different to the very low influence responses and also high irradiance reaction. You need to know that we have phytochrome and we also have cryptochromes. This cryptochrome is actually mediated the growth response to blue and UVA. So they actually respond to different light or different spectrum of light. As this cryptochrome, okay, they are for the blue and UVA light. And example of blue light photoreceptor for these cryptochromes is cytochrome 1 or cry1 and cry2. Now we go to the developmental responses mediated by phytochrome and cryptochrome. So for these development responses, we look on the seed germination. Okay, because seed germination they influenced by light. Seed germination is influenced by light. So when the seed actually stimulated by light, we call as positively photoblastic seed. So if that seed is negatively photoblastic, means that seed is inhibited by high fluence rate light exposure. At the same time, phytochrome also not serve only for the seed germination, but this phytochrome can act as sensor, where it can give seed able to determine their depth in the soil. And now we look on still developmental responses mediated by phytochrome and cryptochrome, but we look on the deethyolated plant. Just now we look on ethyolated. Now we look on deethyolated, which is for ethyolated, the plant grow in the dark condition. If deethyolated means we take the dark plant, the plant that grow in the dark condition, we expose to the light. So because of that, we call as deethylation. Okay, so we can see their specific changes that will be occur to that ethyolated plant. So we can see the changes actually occur to the hypocotyl growth, okay, which is it will be stopped, and also at their vertical growth can be occur. Okay, at the same time, the leaf also unfold and enlarge. At the same time, the chloroplast will be mated and they are synthesis the chlorophyll. So this will make the leaf will be green color, which is because from the ethylated to deethylated. So in the dark condition, and then after that they expose that plant in the light. Now we look on the shading trigger changes in plant growth. So if a plant they have a shading effect, it will be show the shade avoidance syndrome. So they have a name, okay, for that response toward the shading effect, which is shade avoiding symptoms. So one of these syndrome is it will be increase the specific leaf area, which is it will be increase the surface area of the plant, and at the same time the chlorophyll level also will be increased. So it will be also increase the capability of that chlorophyll to harvest the light. And they have some changes in their growth and also to their morphology, which is it will be alter the position of leaf to increase access to light. You need to know that shading response actually is initiated because of light environment is far right and rich. Means at that environment they have a high concentration of PFR. Okay, so in this condition, cryptochrome and phytochrome P this condition, cryptochrome and phytochrome B, D, and E will be used to discriminate between shading and full light condition. So effect from the shading, it will be described, okay, in terms of the PR-PFR ratio. This slide show you the growth of the plant responses to the light condition, where it's controlled by the ratio of PR and PFR. So the picture show you the Chenopodium album, which is the plant species that exposed to far red light, and it will be increase the stem extension. And we can say as a conclusion, they have a linear relationship between PFR and PR ratio. That's all for today.
어느 날 세상이 멈춰서 아무런 예고도 하나 없이 꿈은 기다림을 몰라서 눈치 없이 와버렸어. 자국이 지워진 거리 여기 남아져 있는 나 혼자 가는 시간이 미안해 말도 없이
오늘도 비가 내릴 것 같아 흠뻑 젖어버렸네. 아직도 멈추질 않아. 저 먹구름보다 빨리 달려가. 그럼 될 줄 알았는데 나 겨우 사람인가 봐. 몹시 아프네. 세상이란 놈이 지갑기 덕분에 눌러보는 먼지 쌓인 되감기. 넘어진 채 청하는 엇박자의 춤. 겨울이 오면 내 진짜 더 뜨거운 숨.
끝이 보이지 않아. 출구가 있긴 한가. 발이 뜨지 않아. 잠시 두 눈을 감아. 여기 내 손을 잡아. 저 미래로 달아나자. 따끈하거든 the forest. 하루가 돌아오겠지. 아무 일도 없던 듯이. Yeah, life goes on like an arrow in the blue sky. 또 하루도 나다겠지. On my pillow, on my table. Yeah, life goes on like this again. 이 음악을 빌려 너에게 나 전할게. 사람들은 말해 세상이 다 변했대. 변할까